So welcome back to thin linear wire antennas, another part. So in the last part, we have seen the introduction for this thin linear wire antennas. So here we can see continuation for this, that we have seen the basic elements, different types for the thin linear, and we have seen the Hertzian dipole or current element, placing the current element on the z-axis, and we have seen the field components representation on the figure as a graphical, and we have obtained the vector potential as a final value in terms of r, theta, and phi. In continuation to that, we have obtained the magnetic field strength, that is h bar, using vector potential a bar, and simplifying that, we get the h in terms of phi component, and the two terms are 0. And then we have started the electric field strength representation using the Maxwell's equations. Del cross h bar is equal to j bar plus dou d bar by dou t. Here we make that j bar current density is 0, and replacing dou by dou t as a in frequency domain j omega epsilon. Then we obtain this equation. So let us extract deriving separately del cross h bar in terms of spherical coordinates, that is del cross h bar is equal to 1 by r square sine theta into the components ar, r a theta, r sine theta a phi, dou by dou r, dou by dou theta, and dou by dou phi, and field components h r, r h theta, r sine theta, h phi. If we expand these terms, we can get an equation. But before proceeding to that, the previous we can see that hr and h phi components are 0. So substituting those components here, we get simplified value, that is h del cross h bar as del cross h bar is equal to 1 by r square sine theta into ar dou by dou theta into r sine theta h phi minus r a theta into dou by dou r sine theta h phi. It is expanding the above terms we are doing now, and we get the final term is 0. So this is the final term, we get it. Has this, if we see, the terms has two field components, that is r component and theta component. So as h is representing only phi component, E is representing r as well theta component. So we'll derive separately considering r component and theta component separately. Substituting this here in E, then we can extract separately. So let us proceed to that. So let us take only ER component first. So we have the scaling factor of 1 by j omega epsilon here, you can see. So and considering only the r component, then we can get 1 by r square sine theta dou by dou theta into r sine theta h phi. So substitute h phi component from the previous slides. So then j omega mu, j omega epsilon into 1 by r sine theta dou by dou theta into j k I naught L sine square theta divided by 4 pi r into 1 plus 1 by jkr into e power minus jkr. This is the term we get. So as look on to this equation, the theta term is only the dependent, remaining all are independent term to the differentiation. So we have the term sine square theta is the dependent. So just like if you take x square differentiation 2x, just like that, you can have the terms here for the differentiation 2 sine theta, that is for the sine theta differentiation. Once again, you can get cos theta differentiation for this. Then we can get the equation for this here as 1 by j omega epsilon into r sine theta into j k I naught L into 2 sine theta cos theta divided by 4 pi r into 1 plus 1 by jkr into e power minus jkr. So let us replace the terms of k, omega, epsilon in terms of intrinsic impedance as neta is equal to k by omega into epsilon. Here, k is phase constant, omega is angular frequency, epsilon is permittivity. So we get the field component of E in terms of R as neta I naught L cos theta divided by 2 pi r square into 1 plus 1 by jkr into e power minus jkr. This is the final term for the r component. Let us proceed for theta component of electric field intensity. So E theta is equal to 1 by j omega epsilon into del cross h bar only for the theta. So then we can write j omega epsilon into 1 by r square sine theta into minus r sine theta dou by dou r into r h phi. So this term we have been writing from the previous slides. Then 1 by j omega epsilon, and there are certain terms will get cancelled and substitute h phi component from the past slides. Then we can get 1 by r into minus dou by dou r into substituting the h phi component as r j k I naught L sine theta by 4 pi r into 1 plus 1 by jkr into e power minus jkr. So after doing the differentiation, as the differentiation here is with respect to r, so the terms will be there here 1 by j omega epsilon, and there are certain common terms is also there. So let us make that common term here. That is minus j k I naught L and sine theta. All these are independent terms for the differentiation. So with that consideration, we are writing everything outside the differentiation. 4 pi into dou by dou r is the only differential term. It is e power minus jkr in this, and then plus e power minus jkr by jkr. These are the terms dependent for the differentiation. So here in the first term is just like e power x differentiation. Here we have the differentiation with the u by v rule. So you can write, apply differentiation in the denominator with the v square. Denominator in the numerator has v u dash minus v u v dash. So after simplifying this differential term, we can get the final term with replacing k, omega, and epsilon as neta, that is intrinsic impedance as k by uh, omega epsilon is equal to neta. Then we can get as neta I naught L sine theta into jk by 4 pi r into 1 plus 1 by jkr minus 1 by kr whole square into e power minus jkr. So this is the final electric field component theta for the current element or the infinitesimal dipole or Hertzian dipole. Now let us see the other parameter of the same wire antenna, that is the power density and radiation resistance. Power density and radiation resistance. So the input impedance of an antenna, which consists has a real part as well imaginary part, we can write the antenna impedance as ZA is equal to RA plus JXA. So we have where RA is a antenna resistance. So that is equal to, we can have the terms here, radiation resistance as well loss resistance that will be considered here. And to find the input resistance for a lossless antenna, Poynting vector is found in terms of electric field and magnetic field radiated by the antenna. So the power for this Hertzian dipole, we use the complex Poynting vector, that is a P is equal to E cross H. The average value of the Poynting vector, we can consider P is equal to 1 by 2 into E cross H, the star. Star represents the complex conjugate, that as both E and H always perpendicular to each other, they are not at the same directions, and the propagation of those two will be perpendicular. We have transverse electromagnetic nature here. So from the previous slides, the field components HR, H theta is equal to 0, and we have the E phi component is also 0. And we will write this E and H as a matrix representation of the spherical coordinates AR, A theta, A phi, ER, E theta, E phi. And we have HR, H theta, and H phi. So from this previous slides, we can see that these field components are 0. Make necessary field components is 0, that your E phi is 0, HR is 0, and H theta is 0. Substituting that and expanding the power, we can get 1 by R into AR into E theta H phi minus A theta into ER into H phi. We would mark this as equation number 1. And in equation 1, the first term represents the radial component, that is denoted as PR, and the second term represents transverse components P theta. And in order to identify the radiation resistance, radial component plays very important, as theta is much near to the antenna elevation angle. R is at far distance where the point P, observation point P, is considered. So PR plays very important in evaluation radiation resistance. At that time, we'll consider only PR. Now, let us identify PR, P theta separately. So now for PR, I'll write the equation PR is equal to 1 by 2 into as a field component AR, substituting the value of PR. So we got a PR value is equal to, I am writing here, 1 by 2 into AR into E theta into H phi, the star. The star represents complex conjugate. So wherever there is a term, so J should be written as a minus J, or if it is a minus J, then replace as plus J. I'll do that. So J K neta I naught L sine theta by 4 pi r into 1 plus 1 by jkr minus 1 by kr whole square into e power minus jkr. This is one term. And the product term, that is h phi, as minus j, as I said that so complex conjugate, you have to replace the corresponding terms plus j as minus j and minus j as plus j. That should be written here. So sine theta into 1 plus 1 by minus jkr into e power jkr. So these are the terms we get here. So this complete term is E theta. This complete term is H phi conjugate. So we can get it that here the star is to be placed. Star is to be placed here. If we simplify this equation, taking the common terms as from the both ER, E theta and H phi, we can get the value as PR is equal to neta k square I naught square L square sine theta sine square theta divided by, we have the term 32 pi square r square here. That is, we have the term in the outside the parenthesis 2, 4 and 4, 16, 32. The terms, remaining terms which are not in common is writing now 1 plus 1 by jkr minus 1 by kr whole square into 1 minus 1 by jkr. This is the term. If we multiply these two terms, we can get the simplified term. There are certain terms will get cancelled. Then we can get neta k square I naught square L square sine square theta divided by 32 pi square r square into 1 minus j by k cube r cube. And if we just rearrange these terms with replacing with the assumption that lambda is equal to 2 pi by k, as then we can get the power in radial direction as neta by 8. That 32 is split into two parts, theta by 8. And we get the value of remaining, that is I naught L by lambda as a whole square. And we have the other term sine square theta by r square into the last term as 1 minus j by kr whole cube. So this is the power for the radial component. Similarly, we will do the power for the transverse component P theta. Let us do that. So P theta is equal to minus 1 by 2 ER H phi conjugate. That is equal to minus 1 by 2 into neta I naught L cos theta divided by 2 pi r square into 1 plus 1 by jkr into e power minus jkr minus j into k I naught L sine theta divided by 4 pi r into 1 minus 1 by jkr into e power jkr. So the second term is the conjugate. So you have to make that conjugate term as imaginary terms is to be magnitude sign is to be changed. So these are the two signs. After simplifying, taking the common terms, we can get p theta is equal to j neta k I naught L whole square into cos theta sin theta divided by 16 pi square r cube into 1 plus 1 by kr whole square. This is the value of the transverse component of the power. So in order to obtain the radiation resistance, we'll write the power for the radial component as a P radiated suffix PRAD, and it is been integrating for the term of 0 to 2 pi for the phi component, 0 to pi for the theta component. PR is representing the radial component, and r square sine theta d theta d phi is using the spherical coordinates for the closed surface is being considered here. So substituting the PR in this equation, so we'll assign some equation number for PR as equation number 2 and this as equation number 3. Substituting equation 2 in 3, then we have P radiated is equal to 0 to 2 pi, 0 to pi, neta by 8, I naught L by lambda whole square, sine square theta by r square into 1 minus j by kr whole cube into sine theta r square d theta d phi. So in order to simplify easily this integration, there are no d phi terms in this integration, but we have the dependent terms of theta is only sine theta. So as there are two sine components are here, sine square and sine theta will become sine cube. So let us do that simplified easily. That is considering sine 3 theta formula, that is sine 3 theta is equal to 3 sine theta minus 4 sine cube theta. So from this, again, this is a trigonometric relation. Sine cube theta is equal to 3 sine theta minus sine 3 theta by 4. So we will mark this as equation number 4. So we have been extracting the equation 4, deriving only sine cube theta in a simplified manner. So now integrate this sine cube theta with the corresponding intervals. Then we can get 1 by 4 into 0 to 2 pi, 0 to pi, 3 sine theta minus sine 3 theta into d theta d phi. So after integration, we can get the term for the phi. There is no dependent terms. So you can get directly integral 1 d phi as phi. Substitute the limits 2 pi minus 0, then you can get 2 pi. And for the theta component, minus 3 cos theta plus cos 3 theta by 3 for the integration, and the limits is pi, 0 to pi. Substituting the limits, we can get the final value for this is 8 pi by 3. So substitute this in equation 4. Then we can get equation 4, that is a P radiated component, neta by 8, I naught L by lambda whole square into 1 minus J by KR whole cube into 8 pi by 3. So the term 8 is get cancelled here. Then finally we obtained P radiated is equal to neta pi by 3. Let me erase this one. It is neta pi by 3 into I naught L by lambda whole square minus neta I naught L by lambda whole square into pi by 3 into J by KR whole cube. From this equation 5, we can get that the first term is the radial component of the real part. The second one is the radiated power of imaginary part. Now we'll take the radiated power in only the real part, the magnitude. Then we can get neta pi by 3 into I naught L by lambda whole square equal to 1 by 2 into I naught square into RR. Here we have made the terms neta, pi, 3 and L lambda. All those terms are considered to be RR. RR is called radiation resistance. Here the real term represents the power radiated from the surface of the sphere in radial direction. As the imaginary term is negative, the reactance of the infinitesimal dipole is capacitive. So, and here your RR term is 2 neta pi by 3 into L by lambda whole square. So, from the basic concepts of the wave propagation, neta is here intrinsic impedance and the value is 120 pi. That is in terms of numerical value, it is 377 ohms. If we substitute that neta as 120 pi here, then we can get the radiation resistance for the current element or infinitesimal dipole, Hertzian dipole, as 80 pi square L by lambda whole square. So this is most important for many exams or computer exams or theory exams. Evaluating radiation resistance is very important. That represents is related with respect to length as well, the wavelength lambda. So this has to be obtained from the basic vector potential for placing current element in along z axis. Thank you.